13 billion years ago, the universe broke its own rules. It was still an infant, barely 500 million years old, emerging from the last shreds of cosmic darkness. Then, out of nowhere came light, not faint stars or tiny clusters, but full-grown galaxies, massive, blazing, ancient-looking islands of stars. James Webb just spotted more than 300 of them. They burn a deep, blood red in the infrared, ghosts from the dawn of time. Each one holds billions of stars that by every law of physics should not yet exist. There wasn't supposed to be enough matter, not enough time. Dark matter halos hadn't even fully formed. Hydrogen fog should have drowned their light completely. Yet there they are, bright, defiant, and impossible. These galaxies don't just challenge our understanding of cosmic history, they rewrite it. So if you love mysteries that bend the edges of science itself, hit that like button and subscribe, because what James Webb just revealed may change everything we thought we knew about the beginning of the universe. Picture a newborn baby speaking in full sentences minutes after birth. That's what James Webb just witnessed in the early universe. Galaxies behaving far too mature for their age. Astronomers at the University of Missouri were scanning 4 tiny windows of deep space when they stumbled upon something extraordinary. 300 glowing objects so bright, they shouldn't exist that far back in time. These weren't just distant galaxies, they were cosmic paradoxes. Here's why this discovery shakes the foundations of physics. When you look deep into space, you're actually looking back in time. Light takes billions of years to reach us, so every distant speck is a window into the ancient past. These objects sit so far away that we're seeing them as they were just 500 to 700 million years after the Big Bang, when the universe itself was still in its cosmic infancy. According to every established law of astrophysics, galaxies need time to grow. Stars form slowly from collapsing clouds of hydrogen and helium. Gravity pulls matter together grain by grain, shaping galaxies over millions of years. Dark matter, halos, must first form an invisible skeleton that ordinary matter can cling to. Everything follows an orderly sequence. Small structures first, then larger ones. But these 300 galaxies broke that script completely. They're shining with the brilliance of fully formed galaxies, packed with billions of mature stars, some nearly as massive as our own Milky Way. Imagine walking into a field you planted yesterday and finding a fully grown oak forest waiting for you. That's how wrong this timeline looks. The research team, led by astronomy professor Hao-Jing Yan, calls them candidate galaxies, because scientists still need to confirm exactly what they're seeing. Right now, they appear as faint red dots in Webb's infrared images. But those tiny crimson specks carry spectral fingerprints of enormous, thriving stellar cities that shouldn't be there. Their discovery shakes the core of the Lambda CDM model, our most trusted blueprint for how the universe evolved. According to this model, small galaxies are supposed to form first, slowly merging into larger ones. Baby stars come before ancient populations, but these early giants flip that logic upside down. They suggest the young cosmos was far more chaotic, more creative, perhaps even governed by processes we don't yet understand. Over 80% of these mysterious objects belong to a category called extremely red objects, glowing intensely in specific infrared wavelengths. Their redness tells astronomers they're incredibly distant and ancient, but it also hints at something even stranger. They became bright and massive too fast. Something in the newborn universe was jump-starting galaxy formation at an impossible rate. Some unknown force or condition, a kind of cosmic accelerator, was working far beyond anything our physics can currently explain. Before these impossible galaxies could exist, the universe was smothered in darkness. Not the darkness of a night sky, but a pure cosmic blackness. No stars, no galaxies, just cold hydrogen gas stretching endlessly through space. This cosmic dark age began about 380,000 years after the Big Bang, when the universe cooled enough for electrons to finally join with hydrogen nuclei, forming the first neutral atoms, a process called recombination. Before this moment, space was an opaque plasma, so dense that light couldn't travel more than a few feet without scattering. Then, slowly, light broke free, and the first stars ignited. But what James Webb has now seen suggests that light might have risen far sooner and far more powerfully than we ever imagined. Something in those first billion years changed the rules of creation itself. When the first neutral hydrogen formed, something extraordinary happened. Photons were finally free to move. For the first time in cosmic history, the universe became transparent. But there was a catch. No new light existed yet. The initial glow of the Big Bang was still racing outward, thinning and fading as space itself expanded. Within a few million years, that glow dimmed into nothing. The cosmos fell into total darkness. Imagine drifting through this silent void. In every direction, there is only blackness. No stars burn. No nebulas shimmer. The universe is filled with a thin, invisible mist of neutral hydrogen, absorbing any trace of ultraviolet light. Even the rare photon that tried to escape was trapped, swallowed by the gas before it could travel any real distance. And yet, something unseen was already shaping the future. Dark matter. It doesn't interact with light, but its gravity was hard at work, pulling the hydrogen into filaments and clumps. These invisible structures, dark matter halos, were quietly building the framework for galaxies yet to come. All of this happened in total silence. No light, no sound. Just the slow, patient pull of gravity sculpting the first blueprints of creation. This age of darkness lasted hundreds of millions of years, somewhere between 400 and 600 million. We can't observe it directly. Light from that period never reaches us. The hydrogen fog absorbed it all. What we know comes from simulations and from the faint clues left behind in later cosmic light. During this time, the temperature of space plummeted close to absolute zero. The drifting hydrogen gas grew unimaginably cold, around minus 450 degrees Fahrenheit. The universe was vast, still, and waiting. Yet beneath that calm, gravity never stopped working. Dense pockets of dark matter drew in more gas, compressing it tighter and tighter. Pressure built inside these collapsing clouds until, at last, something spectacular happened. The first stars ignited. These were no ordinary stars. They were colossal, hundreds of times more massive than our sun, burning white-hot and living fast. Composed purely of hydrogen and helium, they lived only a few million years before exploding as violent supernovas. But in their brief lifetimes, they changed everything. Their searing light tore through the hydrogen fog, ending the long cosmic night. The Dark Ages were over, and astonishingly, within just a few hundred million years of that first light, entire galaxies, hundreds of them, were already shining across the newborn cosmos. The timeline feels impossibly tight, almost as if the universe had sprinted instead of crawled toward complexity. James Webb isn't just a telescope, it's a time machine. It captures light that has been traveling across the cosmos for nearly the entire age of the universe. When it peers into deep space, it's not seeing distance, it's seeing time itself. Here's how that works. Light moves incredibly fast, at about 186,000 miles every second. Yet over cosmic distances, even that speed isn't instantaneous. The nearest star beyond our sun lies more than 4 light years away, meaning its light takes 4 years just to reach us. We never see stars as they are, only as they were. Now stretch that idea to galactic scales. The 300 mysterious galaxies Webb found are roughly 13 billion light years away. Their light began its journey when the universe was barely 500 million years old. When we look at them today, we're witnessing a chapter of time that ended long before Earth even existed. But there's another twist. The universe isn't static, it's expanding. Space itself stretches like rising dough, and the light traveling through it stretches too. This stretching shifts the light toward the red end of the spectrum, a phenomenon known as redshift. Think of an ambulance siren. When it approaches, its sound waves compress and the pitch rises. As it speeds away, the waves stretch and the pitch drops. Light behaves the same way. Galaxies moving away from us have their light stretched into longer, redder wavelengths. For the most distant galaxies, this redshift is extreme. Light that once blazed in ultraviolet or brilliant blue now arrives as faint infrared, the color of cosmic memory. And that's exactly what James Webb sees. The faded, stretched heartbeat of ancient galaxies that shouldn't exist so soon after the dawn of time. The Hubble Space Telescope, as powerful as it is, was never built to see this far back in time. It captures light mostly in the visible and ultraviolet ranges. Beautiful, but limited. The earliest galaxies are so distant that their light has been stretched far beyond those wavelengths. They've redshifted into the deep infrared, completely invisible to Hubble's eyes. That's why the James Webb Space Telescope was created. It's not just a telescope, it's a cosmic archaeologist. Its 18 gold-coated hexagonal mirrors collect faint whispers of infrared radiation, light that has been traveling across the universe for more than 13 billion years. Webb's instruments can detect wavelengths between 0.6 and 28 micrometers, the perfect range to reveal galaxies whose ancient light has been stretched by the expansion of space itself. By measuring how much a galaxy's light has redshifted, astronomers can determine its distance, and in turn, how long ago its light began the journey toward us. A galaxy with a redshift value of 10, for instance, existed roughly 13.2 billion years ago. The higher the redshift, the older the galaxy. Webb's near-infrared camera, NIRCam, captured the 300 mysterious galaxies during a series of deep-field surveys. Long, patient exposures of what appear to be empty patches of sky. What looks like darkness to our eyes becomes a glittering sea of ancient galaxies in Webb's view. Each of those 300 red dots represents a galaxy so far away that its light began its journey before the Earth existed, before the Sun was born, before most of the stars in the Milky Way had even formed. These are the lights of the cosmic dawn itself. But here's the puzzle. These galaxies shouldn't be there. Not yet. According to our models, the universe was far too young for so many massive galaxies to already exist. To uncover them, astronomers used an ingenious strategy known as the dropout technique, a kind of cosmic detective method built on the physics of hydrogen. Here's how it works. Hydrogen atoms absorb ultraviolet light at a very specific wavelength, known as the Lyman limit, around 91.2 nanometers. When ultraviolet light from a distant galaxy passes through the hydrogen clouds of the early universe, all wavelengths shorter than that limit are absorbed. The result? The galaxy drops out of visibility in those bluer wavelengths. To detect this effect, astronomers take multiple images of the same patch of sky using different filters, each tuned to a specific color or wavelength. If a galaxy appears bright in the redder or infrared filters, but completely disappears in the bluer ones, that's the telltale dropout signature. It means the galaxy's light has been stretched, redshifted, by an enormous distance. Bangjiang Sun and Haojing Yan, leading the University of Missouri research team, used this method on Webb's data. They analyzed over 500 square arc-minutes of sky captured by NIRCam, looking specifically for objects that vanished in shorter wavelengths, but shone brightly in longer ones. This disappearing act acts as a cosmic fingerprint, an unmistakable sign of galaxies from the universe's earliest ages. The farther away the galaxy, the more its light stretches. At a redshift of 7, the Lyman break shifts into the near-infrared. Beyond a redshift of 10, it moves even deeper into the infrared range. By comparing how the same object behaves across multiple filters, astronomers can estimate how far the Lyman break has moved, and therefore how ancient the galaxy truly is. But the dropout method isn't perfect. Other objects can mimic the same effect. Dusty, nearby galaxies can appear red for different reasons. A quasar or an active black hole might produce similar colors, tricking the data. That's why these are called candidate galaxies, not confirmed ones. Further spectroscopic analysis will be needed to prove exactly what they are. Still, the results stunned the scientific community. Using this technique, the researchers found 300 candidates showing the dropout pattern. Each glowed brightly in certain infrared wavelengths, while vanishing completely in others. Their redshift signatures suggested they formed astonishingly early in cosmic history, within the first few 100 million years after the Big Bang. And yet, something doesn't add up. The number of bright galaxies found was far higher than any model predicted. According to our best theories, the early universe shouldn't have produced so many massive galaxies, let alone ones glowing with such intensity. These weren't faint smudges hiding at the edge of detection. They were radiant, bursting with light, suggesting each one contained billions of stars. Somehow, the infant universe assembled colossal stellar cities faster than physics should allow. The dropout technique revealed more than distant galaxies. It uncovered a mystery that may force us to rethink how the cosmos grew from darkness to light, and how, against all odds, it built complexity long before it was supposed to. The early universe seems to have built galaxies far faster than physics should have allowed. When you look at the 300 mysterious objects discovered by James Webb, one thing stands out immediately: their color. not pink, not orange, but a deep blood red glow that dominates the image. This color isn't an artistic flourish, it's a crucial clue to their identity. Over 80% of these galaxies fall into a category astronomers call extremely red objects. In scientific terms, their light is about 6 times brighter in longer infrared wavelengths than in shorter ones. A huge difference that tells a powerful story, because in astronomy, color is time. Young stars burn hot and blue. They flood space with ultraviolet and visible light. Older stars, cooler and more bloated, glow red. Normally, a red galaxy means its stars have aged, its youthful fires long burned out. But these galaxies are not old. They're ancient in location, not in time. They existed when the universe was still in its cosmic childhood. Their redness isn't from age, but from the redshift, the stretching of light as the universe expands. As that light travels billions of years across the expanding cosmos, its wavelengths lengthen. Ultraviolet light becomes visible red. Visible red becomes infrared. The farther away a galaxy is, the more extreme the shift. For galaxies at redshifts of 7 to 10, light that began as ultraviolet now shines only in the mid-infrared, exactly where Webb is most sensitive. In fact, Webb's mid-infrared instrument revealed extra detail in 137 of these galaxies, confirming that their light has been stretched beyond recognition. But there's another ingredient that might deepen their red hue: cosmic dust. Dust scatters and absorbs blue light, letting red light pass through more freely. So if these galaxies already contain large amounts of dust, that would make them appear even redder. But that explanation raises a troubling question. How could dust exist so soon after the Big Bang? Dust is built from heavy elements: carbon, silicon, iron, the ashes of dead stars. Those elements don't exist in pristine hydrogen gas clouds. They're forged in the hearts of stars and scattered. When those stars explode as supernovas, that process takes time. Several generations of stellar birth and death. Yet for these galaxies to already be dusty means that stars had to form, live, die, and enrich the cosmos with metals in just a few 100 million years. That's an almost impossible rate of stellar evolution. It suggests these galaxies were forming stars at speeds far beyond anything seen in the modern universe. This redness also allows astronomers to measure how far away and how old each galaxy is. By identifying which wavelengths each galaxy drops out of, researchers can calculate its redshift, a cosmic fingerprint of distance and age. For these 300 candidates, 2/3 seem to sit at redshifts between 1 and 4, meaning they're relatively closer and younger than first thought. But the remaining third lie far beyond that, at redshifts above 7, possibly even 10. Those are the truly shocking ones. If confirmed, they would represent massive galaxies forming when the universe was less than 500 million years old. Galaxies filled with billions of stars, born long before they should have had the time or materials to exist. That deep red glow, then, is not just beautiful. It's a warning that our understanding of cosmic history may be incomplete. These galaxies appear to have skipped several steps in the known sequence of cosmic evolution, assembling themselves at impossible speed. To grasp how astonishing that is, you have to understand what it takes to build even a single star. Star formation begins in giant molecular clouds, vast, cold regions of gas and dust drifting through space, made mostly of hydrogen, with a sprinkling of helium and trace elements. These clouds slowly collapse under their own gravity. Denser pockets form inside them. As each pocket contracts, it heats up. When its core temperature reaches around 18 million degrees Fahrenheit, nuclear fusion ignites, and a star is born. Normally, that process unfolds over millions of years. Then, millions more pass before those stars die and seed the universe with heavier elements. But in these ancient galaxies, that timeline seems compressed, like the universe was fast-forwarding through its own evolution. In other words, the blood-red galaxies Webb found are more than distant lights in the void. They're evidence that something about the early cosmos, gravity, dark matter, or even the laws of star formation worked very differently than we thought. Star formation might seem simple. Clouds of gas collapse, ignite, and shine. But the process is anything but limitless. Physics enforces strict speed limits on how quickly stars can form. The main barrier is something astronomers call feedback, nature's built-in braking system. When massive stars are born, they unleash torrents of radiation and fierce stellar winds that blast the surrounding gas away. That same gas is the raw material needed to make more stars. Supernovas then add to the chaos, scattering even more matter into space. This feedback prevents galaxies from turning all their gas into stars at once. It acts like a pressure valve, slowing star formation to a sustainable pace. Without feedback, a galaxy could burn through its fuel in a few million years. A brief cosmic flash before fading into darkness. With feedback, the process stretches over billions of years, creating the long, steady evolution we see in modern galaxies. Today, our Milky Way forms only about 3 new solar masses of stars each year, a modest pace. More active galaxies might produce 10 to 20 solar masses annually. The most extreme starburst galaxies can briefly reach 100 solar masses per year, but such frenzied bursts don't last long before feedback shuts them down. Now compare that to the galaxies Webb has found. If these 300 mysterious objects truly contain as many stars as the Milky Way, roughly 100 billion, and if they reach that mass in just a few 100 million years, the numbers become staggering. Building 100 billion solar masses of stars in only 500 million years would require an average star formation rate of about 200 solar masses per year, every year, for 500 million years straight. That's 10 to 20 times faster than the most extreme starbursts we've ever observed. And those modern galaxies usually burn out within a fraction of that time. So how did these early galaxies sustain such impossible growth without collapsing under their own energy output? Somehow, they either evaded or overpowered the very feedback mechanisms that should have stopped them. One idea is that star formation itself worked differently in the early universe. The gas back then was denser, untouched by heavy elements like carbon or iron that now fill modern galaxies. This primordial gas might have collapsed more efficiently under gravity, forming stars faster than enriched gas does today. Another theory suggests that the first stars didn't form alone, but in massive clusters, huge swarms of newborn suns forming together, merging their heat and gravity to accelerate the process. Some researchers even propose that these galaxies didn't form stars steadily at all. Instead, they may have experienced short, violent bursts of activity, episodes when star formation spiked to over 1,000 solar masses per year, then quieted down before roaring back again. A few cycles like that could build up their massive stellar populations surprisingly quickly, but each of these explanations demands something that current cosmological models don't include: extreme conditions or physics we haven't yet seen. The standard theory assumes galaxies grow gradually, with feedback keeping things in check. The Webb discoveries tell a very different story, one where the early universe was more chaotic, more productive, and far more mysterious than we imagined. And the puzzle doesn't end there. Every galaxy we know today sits inside an invisible structure, a halo of dark matter. Dark matter doesn't emit light or interact with atoms, but its gravity sculpts the universe. It holds galaxies together and guides how they form. According to our models, these dark matter halos take time to assemble. About 500 million years after the Big Bang, they should have been tiny, not yet strong enough to host galaxies as large as the ones Webb found. That's a serious problem. Dark matter makes up roughly 84% of all matter in the cosmos. It formed shortly after the Big Bang, probably as exotic particles that we still haven't identified. At first, it was evenly spread through space like a fine mist, but gravity slowly pulled that mist into denser regions, a process astronomers liken to cream swirling into coffee. Tiny irregularities grew stronger over time. Denser patches of dark matter pulled in more of their surroundings, forming clumps that grew larger and heavier. These clumps became gravitational wells, invisible frameworks into which hydrogen and helium gas could fall. Once that gas condensed at the center, stars ignited, and galaxies began to take shape. This growth followed a hierarchical pattern. Small halos formed first, giving rise to dwarf galaxies. Over billions of years, those dwarfs merged, creating larger and larger systems, eventually producing galaxies like our Milky Way. But the galaxies Webb has found don't seem to fit that sequence at all. They appear to have skipped the early stages, forming huge, mature systems long before dark matter halos should have been massive enough to support them. Something, somewhere, isn't adding up, and whatever that missing piece is, it may rewrite our understanding of how the universe built its first galaxies. By the time the universe reached its present age, Vast dark matter halos had fully assembled, supporting enormous galaxies like our Milky Way. But such cosmic architecture takes time to build. Simulations of the early universe show that halos massive enough to cradle Milky Way-sized galaxies shouldn't have existed until at least a few billion years after the Big Bang. At just 500 million years, post-Big Bang only small, primitive halos should have been around, the humble beginnings of what would later merge into grand galaxies. Yet the 300 mysterious objects detected by the James Webb Space Telescope appear to be anything but small. They look large, luminous, and mature. Galaxies that seem to have skipped the entire childhood of the cosmos. If these findings hold true, it means these ancient giants sit inside dark matter halos that shouldn't have had enough time to grow, and that, as cosmologist Claudia Lagos bluntly put it, poses significant challenges to our standard model. Under the Lambda CDM cosmological framework, our best model of how matter evolves, dark matter halos follow a predictable growth rate. They start small, merge, and slowly form the gravitational scaffolding that galaxies require. But these early behemoths outpace those predictions by a staggering margin. How could that be? A few explanations have surfaced, none entirely satisfying. Perhaps dark matter clumped together more quickly in some regions, amplified by random density fluctuations that produce premature cosmic hotspots. Or maybe the physics of the infant universe included exotic processes, unknown forces or particles, that seeded large structures earlier than expected. Another hypothesis goes deeper. Maybe dark matter isn't entirely cold as our models assume. If a portion of it behaved differently, warmer, more dynamic, it might have accelerated structure formation. And then there's a more radical idea. What if these objects aren't galaxies at all? Some astronomers suggest they might be massive black holes surrounded by brilliant accretion disks, immense rings of gas and dust spiraling inward, glowing as they're consumed. A rapidly feeding black hole can shine as brightly as an entire galaxy, imitating its light signature. Black holes can also form faster than dark matter halos, potentially explaining the observed luminosity without requiring mature galaxies. But even this raises new problems. To match Webb's data, these black holes would have to be extraordinarily massive, millions or billions of times the Sun's mass, and they'd need to reach that size in only a few 100 million years. The known pathways for black hole growth simply can't get there that quickly. They'd have to skip multiple evolutionary stages, forming directly as supermassive entities rather than growing from small seeds. In short, the invisible scaffolding of the universe, the dark matter framework that should underlie these galaxies, wasn't ready yet. Either that scaffolding built itself at breakneck speed, or these luminous objects don't rely on it the way we've always assumed. To appreciate how strange that is, consider our own Milky Way. It's an ancient cosmic city, home to roughly 200 billion stars, stretching about 100,000 light-years across. Its formation has been a patient story, a saga spanning more than 13 billion years. The Milky Way's growth began soon after the cosmic dark ages lifted, when light first returned to the universe. Small protogalaxies, each holding only a few million stars, began merging, colliding, and accumulating mass. Over billions of years, these mergers built up the spiral structure we see today. It was a slow, methodical process. The galaxy's central bulge, filled with old red stars, marks its ancient heart, a relic from those first generations. Its spiral arms, by contrast, are relatively young, likely forming only within the last few billion years. Even with such vast timescales, the Milky Way's assembly followed the expected timeline. Dark matter halo first, then gas collapse, then star formation. Now imagine finding something Milky Way-sized when the universe was less than a billion years old. That's what Webb's data implies. Some of these 300 early objects appear to contain tens of billions, perhaps even 100 billion, solar masses worth of stars, yet they achieved this in a few 100 million years at most. What took our galaxy over 10 billion years to accomplish? These ancient systems somehow did in a cosmic blink. To put that in human terms, it's like a newborn reaching full adult size in 1 week. That's the scale of the anomaly, and the differences go beyond speed. Many of these early galaxies have unusual shapes. Flattened disks, clumpy tubes, or chaotic webs of matter. They lack the graceful spiral arms and smooth ellipses that define mature galaxies today. Their structures look raw, unfinished, as though the universe was still experimenting, testing different blueprints for how to build a galaxy. Yet somehow, amid that chaos, they managed to shine with the brilliance of giants billions of years ahead of schedule. If the Webb data is right, then the cosmos itself may have learned to build faster than the laws of physics currently allow. And our entire story of how structure emerged from nothing will need to be rewritten. They look wild and unfinished, more like galactic construction sites than the elegant spiral cities we know today. The Milky Way, for all its beauty, is a product of patience, 13 billion years of slow chemical enrichment. Every generation of stars added heavier elements to the cosmic mix, each supernova seeding the next with richer materials. Our own sun is a third-generation star, built from the ashes of its ancestors. This process was supposed to take time, immense cosmic stretches of it. Yet these ancient galaxies had none of that. They were forged from nearly pure hydrogen and helium, untouched by heavier elements, and still managed to form billions of stars. Somehow, they turned raw, primordial gas into entire galaxies at a pace that defies logic. To grasp how impossible that is, think about our own galaxy. The Milky Way consumed vast oceans of gas over billions of years, losing just as much to supernova explosions and stellar winds. Even after all that, only a small fraction of the gas actually became stars. But these early galaxies, they did it all in a blink, converting gas into stars with astonishing efficiency. They must have retained every wisp of gas, recycling it perfectly, or somehow funneled vast reserves of material inward faster than anything we've ever observed. Compared to the Milky Way, they seem like cosmic paradoxes. Galaxies wearing the faces of the old while existing in the age of the newborn. They are, quite literally, time travelers, showing us a level of galactic maturity that shouldn't have been possible so soon after the universe began. Let's put this into perspective. The universe is 13.8 billion years old. Earth formed about 4.5 billion years ago. Complex life appeared roughly 600 million years ago, and modern humans barely 300,000 years ago. So when we talk about galaxies existing just 500 million years after the Big Bang, we're talking about an era when the universe was barely 3 or 4% of its current age. Imagine compressing all of Earth's 4.5 billion year history into a single calendar year. On that scale, 500 million years would be only 40 days. These galaxies appeared in cosmic January. The universe had barely cleared its throat. In that short window, everything had to happen at once. The cosmic dark ages ended. The first stars ignited. They lived fast and died young, exploding into supernovae that seeded the cosmos with heavier elements. New stars were born from that enriched debris. Gas clouds collapsed and merged. Clusters bound themselves together through gravity. According to our best models, the first stars, those giant, short-lived beacons known as Population 3 stars, formed around 100 million years after the Big Bang. They burned violently, lived briefly, and died in titanic explosions, scattering the first metals into space. By 200 million years, second-generation stars began forming, and by 380 million years, we see the first small galaxies, tiny collections of perhaps a few tens of millions of stars. These were supposed to be the building blocks, the humble beginnings that would one day merge to form grand spirals, like our Milky Way. But what James Webb found shattered that expectation. These 300 mysterious objects existed between 500 and 700 million years after the Big Bang. That's barely 200 to 400 million years after the very first stars ignited. Yet in that unbelievably brief window, they somehow built massive stellar populations rivaling modern galaxies. Consider what that means. Stars take time to form, millions of years per region. To create billions of them, you'd need countless star-forming regions igniting simultaneously, synchronized across the entire galaxy. Clouds of gas collapsing, fragmenting, and lighting up in waves. Even if these galaxies grew through mergers, many small galaxies fusing into one, that too takes time. A single dwarf galaxy might take tens of millions of years to assemble. The mergers themselves often span hundreds of millions more. To fit all of that within 500 million years after the Big Bang is like trying to write an epic novel in an hour, an impossible compression of cosmic history. And yet, there they are, shining defiantly through the veil of time, breaking every timeline, rewriting every theory, and reminding us that the universe still keeps its deepest secrets close. You might expect the first galaxies to be rough sketches, messy, half-formed structures still learning how to exist. But what James Webb found defies that logic. These early systems aren't primitive at all. They look mature, massive, and well-structured, as though they've skipped straight to the advanced stages of galactic evolution. Astrophysicist Joel Leger, who studies these strange objects, described them bluntly: they're bananas. His team expected to find small, blue, baby galaxies at the dawn of time, tiny clusters of newly born stars. Instead, they found deep red, mature-looking systems, galaxies that seem to have leapt millions of years ahead in development. This timeline crisis isn't just about speed, it's about breaking the fundamental limits of physics. Certain cosmic processes can't be rushed: nuclear fusion, gravitational collapse, the cooling of gas. These take time, fixed by the laws of nature. Yet these galaxies appear to have done the impossible. Either our understanding of the timeline is wrong, or these galaxies followed a formation pathway the universe has never revealed before. Out of the 300 early galaxy candidates Webb found, over 240 belong to a mysterious category called extremely red objects. That detail isn't trivial. It's a flashing neon clue. Their extreme redness suggests something profoundly unusual is happening inside them, something beyond the boundaries of normal galaxy evolution. In astronomy, color is data. Light is measured in magnitudes, a logarithmic scale where each step represents roughly 2.5 times more brightness. An extremely red galaxy is more than 2 magnitudes, brighter at longer wavelengths than at shorter ones. That's over 6 times more light in the infrared. Normal galaxies show gentle color gradients. Even the oldest red galaxies near us in the modern universe never reach such extremes. These early galaxies are statistical outliers. So red, they shouldn't exist by our current models. Why are they so red? The first suspect is redshift, the stretching of light as the universe expands. The farther away a galaxy is, the more its light shifts toward the red. At extreme distances, this effect is dramatic. But even when astronomers accounted for redshift, the redness remained too strong to explain. So the next suspect: dust. Interstellar dust absorbs blue light and lets red light pass through, just like how sunsets appear red when Earth's atmosphere scatters blue wavelengths. If these early galaxies contained heavy dust, it could make them appear redder. But here's the problem. Dust doesn't just appear out of nowhere. It's built from heavy elements like carbon and iron, forged in the hearts of dying stars. To have dust, you need multiple generations of stars forming, dying, and exploding. For that to happen in just a few 100 million years after the Big Bang, stellar evolution must have been happening at a breakneck pace. One possible explanation is that the first stars were giants, hundreds of times more massive than our Sun. These titans lived fast and died young, going supernova in just a few million years and enriching their surroundings with metals and dust. If enough of these colossal first stars exploded early, they could have seeded their galaxies with dust in under 100 million years. Another possibility involves stellar population age. When a galaxy experiences a burst of star formation, it initially glows blue from its hot young stars. But those massive stars burn out quickly. As the population ages, the color shifts redder, dominated by smaller, longer-lived stars. If these galaxies had a brief, intense period of star formation, then went quiet, they could appear deep red without needing extreme dust. Astronomers call such systems sleeping beauty galaxies, born in brilliance, then mysteriously dormant. But that raises an even deeper mystery. Why did they stop forming stars so early? Modern galaxies usually shut down star formation when they run out of gas, or when feedback from supernovae or black holes heats or expels their remaining material. Yet in the early universe, hydrogen gas was abundant, everywhere. Nothing should have stopped them. So what did? To answer that, researchers turned to Webb's mid-infrared instrument, MIRI, which can see through dust to peer inside these galaxies. The instrument analyzed 137 of the extremely red objects, confirming something astonishing. These galaxies are not illusions. They are real, distant, and genuinely bright. Their redness isn't a measurement error. It reflects true physical properties that defy conventional understanding. But measuring their distance and age isn't as simple as taking a photo. Astronomers use something called a spectral energy distribution, or SED, a detailed fingerprint of how bright an object is across many different wavelengths. Here's how it works. Different cosmic ingredients leave distinct signatures. Young, hot stars emit mostly ultraviolet and blue light. Older, cooler stars shine red and infrared. Gas clouds heated by star formation glow at specific wavelengths. Dust absorbs short wavelengths and re-radiates longer ones. By collecting data across the entire infrared spectrum, astronomers can map a galaxy's true energy output, revealing its age, composition, and distance. Webb's team built SEDs for all 300 candidates, combining data from multiple instruments and telescopes to get a full picture of their light. Then came the analysis. The spectral energy distribution analysis, SED fitting, for the 300 mysterious objects brought a wave of astonishment. About 2/3 of them turned out to be much closer than first thought, sitting at redshifts between 1 and 4. That places them roughly 2 to 12 billion years in the past. Still ancient by human standards, but not impossibly early in cosmic terms. Those galaxies are fascinating, but they don't threaten to rewrite the laws of cosmology. The real trouble lies with the remaining third. Their SEDs show extreme redshifts, 7, 10, and even higher, meaning they existed less than 700 million years after the Big Bang. These are the galaxies that keep astronomers awake at night. Their light patterns match those of mature systems filled with billions of stars of varying ages. Some of those stars appear hundreds of millions of years old already, which is impossible if the galaxy itself only formed a few hundred million years after the universe began. That would mean star formation started astonishingly early, perhaps within the first 200 million years after time itself began. Even more shocking are their masses. Some of these early objects appear to contain 10 to 100 billion solar masses in stars. That's on par with the modern Milky Way, yet somehow achieved when the universe was still in its infancy. Building that much stellar mass so early would require converting gas into stars with an efficiency far beyond anything observed today. Of course, SED fitting isn't flawless. It depends on theoretical models that might not fully describe the true behavior of early galaxies. If these systems evolve differently from the ones we see nearby, the estimated ages and masses could be off. That's why astronomers are cautious. These are candidate galaxies, not confirmed ones. To truly pin down their distances and properties, scientists need spectroscopy. Spectroscopy is the cosmic truth teller. It splits light into its component wavelengths, revealing distinct lines from specific elements. Each of those spectral lines has a known rest wavelength. By measuring how much those lines have shifted, astronomers can calculate a galaxy's redshift, and therefore its distance, with extraordinary precision. Spectroscopy also uncovers chemical composition, temperature, and density, providing a detailed physical fingerprint. Until those measurements come in, some uncertainty remains. But even without spectroscopy, the SEDs tell a compelling story. A number of these objects are extraordinarily massive, luminous, and formed unbelievably early, pushing the boundaries of what the newborn universe should have been capable of. And then comes the unsettling question. What if these 300 objects aren't galaxies at all? This possibility, as bizarre as it sounds, could solve several problems without defying the laws of physics. The leading alternative hypothesis: they might be black hole stars. Black hole stars are theoretical monsters, cosmic hybrids that shouldn't exist anymore, born only under the extreme conditions of the early universe. Imagine a gigantic primordial star collapsing under its own gravity. Normally, such a star would either explode in a supernova or collapse entirely into a black hole. But in the chaotic environment of the early cosmos, something different might have occurred. As the star's core collapsed, it could have formed a black hole, but instead of devouring the entire star, the black hole became trapped inside it. The core turned into a black hole, while the outer layers remained intact, supported by the enormous energy released as material spiraled into the central singularity. That energy pushed outward, stabilizing the star rather than destroying it. The result? A bizarre hybrid, a brilliant star powered not by nuclear fusion, but by a black hole feeding inside its core. From the outside, it would look like a luminous superstar. On the inside, it would be a cosmic paradox, a black hole wrapped in starlight. Such black hole stars could grow gargantuan, thousands of times larger than normal stars, and shine with an intensity that rivals entire galaxies. This idea gained traction when astronomers spotted strange compact objects in Webb's data, brilliant crimson points of light that didn't behave like ordinary galaxies. Some researchers call them little red dots, They're too small to be galaxies, too bright to be normal stars, and too red to be quasars. Black hole stars could fit that pattern. If the 300 candidates were actually black hole stars, it would explain their impossible brightness and rapid formation. Black holes can grow and radiate energy far more efficiently than stars. They don't need billions of years of gradual evolution. A single black hole star forming within a few million years of the Big Bang could outshine entire galaxies. The numbers add up too. Matter falling into a black hole releases energy far more efficiently than nuclear fusion, turning mass directly into light. A cluster of such objects, each blazing intensely, could mimic the glow of a vast galactic system. But the theory isn't perfect. Black hole stars, if they ever existed, were likely short-lived, collapsing or exploding after just a few million years. Finding hundreds of them at once seems improbable unless they formed continuously across large regions of space. There's also the matter of structure. Galaxies have extended shapes, with light spread over a wide area from billions of stars. Black hole stars would appear as compact points of light. Webb's images hint that some of these objects have real spatial extent, too large to be single stars. And then there's chemistry. Galaxies show spectral fingerprints of many elements: hydrogen, oxygen, carbon, dust. Black hole stars would have a very different chemical and energetic signature, dominated by accretion radiation. Early analyses lean toward the galaxy interpretation, but they don't rule out something stranger. Erica Nelson, one of the astronomers leading the investigation, put it plainly: if these objects turn out to be faint quasars, or some entirely new kind of object, that would be just as extraordinary as finding impossible galaxies. The truth may lie somewhere between. Some of the 300 could be genuine early galaxies, massive, fast-forming systems that challenge our cosmic models. Others might be misidentified quasars or active galactic nuclei, and perhaps, just perhaps, a few are relics of a forgotten era. Black hole stars that briefly lit the young universe like cosmic lanterns. Whatever they are, one fact remains. The discoveries have shaken our understanding of cosmic dawn. Because in that first billion years, when the universe should have been quiet and dark, something, galaxy, quasar, or black hole star, was already burning bright enough to pierce the primordial fog and announce that creation had begun. Photons in the early universe didn't stand a chance. Everywhere they went, a wall of hydrogen stopped them cold. The universe was filled with neutral hydrogen, a vast cosmic fog that devoured ultraviolet light. Each hydrogen atom, a single proton with an orbiting electron, acted like a tiny trap. When a photon of just the right energy struck it, the atom absorbed that light completely, kicking its electron into a higher orbit and erasing the photon from existence. This was the age of opacity, when light could barely travel a few hundred light years before being swallowed. To put that in perspective, the nearest galaxy to us today lies over 2 million light years away. No photon from those early galaxies could have crossed that gulf. The cosmos back then was not yet transparent. It was a foggy sea of hydrogen, cold, neutral, and suffocating to starlight. The key to piercing that fog was ionization. If enough energy stripped hydrogen atoms of their electrons, they could no longer absorb light. Ionized hydrogen, free protons without electrons, became transparent. This grand transformation, when the fog began to lift, is known as the epoch of reionization. It began when the first stars and galaxies ignited. Their ultraviolet radiation carved glowing bubbles of ionized space around them. At first, these bubbles were small and isolated, each galaxy surrounded by a sphere of clarity within the fog. But over hundreds of millions of years, the bubbles expanded, merged, and eventually consumed the universe. Light could finally travel freely. The night sky, for the first time, became visible across the cosmos. Astronomers believe reionization was mostly complete around 1 billion years after the Big Bang. But James Webb's 300 mysterious red objects seem to have existed before that process finished, or perhaps during it. They lived in a universe still drowning in hydrogen fog, a time when light wasn't supposed to escape. And yet their glow reached us across 13 billion years. How? Either these galaxies were born in rare regions where reionization began unusually early, cosmic oases of clarity amid the fog, or they were so ferociously bright that even hydrogen couldn't hide them. Their radiation may have burned tunnels through the darkness, carving out transparent corridors in space. In doing so, they might not only have survived the fog, they might have helped end it. If these galaxies were truly that luminous, their ultraviolet light would have blasted nearby hydrogen, ionizing it and creating vast zones of visibility. A whole population of such galaxies could have accelerated the universe's reionization, making it transparent far earlier than models predict. But that leads to a cosmic paradox. We see them because the universe became transparent, yet the universe might have become transparent because of them. Which came first, the light or the clearing? This circular mystery deepens when we compare Webb's view with Hubble's. For 3 decades, the Hubble Space Telescope was humanity's window to the early universe. It captured breathtaking deep-field images, revealing thousands of ancient galaxies frozen in time. It mapped the cosmic dawn, the birth of structure after the Big Bang. But not once did Hubble glimpse these 300 strange objects. Not even a hint. The reason is hidden in the light itself. Hubble was designed to see in ultraviolet, visible, and a sliver of near-infrared wavelengths, from about 120 to 1,600 nanometers. That's perfect for nearby galaxies, or those a few billion years old. But these red-shifted relics from the dawn of time, their light has been stretched by cosmic expansion far beyond Hubble's reach. Light that began as blue, fierce ultraviolet, has now stretched into deep infrared, invisible to Hubble's eyes, but perfectly suited for Webb's. Where Hubble saw darkness, Webb saw ancient fire. Each of the 300 red glows represents a message from the universe's first billion years, light that's been traveling since before our Milky Way even existed. And the fact that this light pierced the hydrogen fog, defying cosmic opacity itself, means something extraordinary happened in those first few 100 million years. Something powerful enough to rewrite our understanding of how the universe woke from its dark age. What we're witnessing may not just be early galaxies. We could be watching the very moment when light broke free, the dawn of transparency, the first cosmic sunrise. James Webb was built precisely to break through the limits that once constrained Hubble. Where Hubble could only see the faint glow of the near universe, Webb was designed to see into the deep, ancient infrared, the wavelengths of light that have stretched across more than 13 billion years of expansion. Its instruments span from about 600 nanometers all the way to 28,000, deep into the mid-infrared range. That's light so red and stretched that Hubble's detectors are simply blind to it. Think of it like tuning a radio. Both telescopes listen to the same cosmic broadcast, but each is tuned to a different frequency band. Hubble could hear the nearby stations, the younger galaxies, while Webb can pick up the ancient frequencies that have drifted down the spectrum over cosmic time. When Webb looked into patches of sky that Hubble had already studied for decades, it didn't just see a little more. It saw an entirely new universe. The same regions that appeared almost empty in Hubble's deepest exposures exploded with luminous red shapes when Webb turned its gaze. What had looked like faint smudges or nothing at all were revealed as blazing galaxies. Their light stretched far beyond the visible spectrum. This wasn't a failure of Hubble. It was simply physics. You can't detect light at wavelengths your instruments weren't built to sense. No amount of clever processing or longer exposure could change that. The photons from these distant galaxies arrived in infrared frequencies that Hubble's detectors couldn't register. They were hidden in plain sight, whispering in a language only Webb could hear. Webb's second great advantage is size. Its primary mirror stretches 21 feet across, more than twice Hubble's 8-foot mirror. That gives Webb over 6 times the light collecting power. The larger the mirror, the more photons it captures, and the deeper it can see into the dark. That difference is transformative. It means Webb can detect faint, ancient objects that would be invisible even in Hubble's longest stare. Some astronomers had predicted that Webb would uncover galaxies beyond Hubble's reach, but few imagined just how many, or how bright, they would be. Webb didn't just find a handful of faint proto-galaxies. It found hundreds, large, brilliant, mature systems that seemed to have formed impossibly early. They weren't supposed to exist yet. Hubble had discovered a few galaxies at redshifts around 7 or 8. Tiny, fragile systems of a few million stars. Exactly what cosmologists expected from the early universe. They were the cosmic infants, flickering at the dawn of time. But Webb's discoveries belong to a different species altogether. They are massive, luminous, and already mature. Like finding fully built cities in an age when only villages should exist. Some contain stellar masses rivaling modern giants like the Milky Way. That's what makes them so astonishing. It's as if the universe went from scattering dust to skyscrapers overnight. Imagine trying to build a vast city out of sand before you even have tools or bricks. That's the paradox of these early galaxies. They seem to have assembled enormous amounts of matter in an impossibly short time. After the Big Bang, the universe was mostly hydrogen and helium, the simplest elements forged in the first few minutes of existence. Roughly 73% hydrogen, 25% helium, and the faintest trace of lithium. Everything else, every heavier element, had to be built later inside stars. Dark matter made up about 84% of all matter, but dark matter can't form stars. It doesn't clump, it doesn't glow. It only provides gravity's scaffolding. Only ordinary matter, the thin gas of hydrogen and helium, could collapse into stars and galaxies. But that gas was spread out, unimaginably thin. Even in regions where quantum fluctuations made it slightly denser, gathering enough material to form a massive galaxy should have taken hundreds of millions of years. Gravity moves slowly on cosmic scales. And yet, these 300 galaxies, some holding the mass of tens or even hundreds of billions of suns, seem to have done it in the cosmic blink of an eye. That's the riddle Webb has placed before us. Hubble showed us the dawn. Webb is revealing that the dawn was brighter, faster, and more furious than anyone dared to predict. The universe, it seems, wasted no time in learning how to shine. But these galaxies didn't gather all that mass in a single cosmic instant, not even close. Modern galaxies like the Milky Way built themselves over billions of years through a slow, patient process of star formation and mergers. Each small galaxy that collided added new material, new stars, and new gas, gradually weaving a vast structure from many smaller pieces. It was a long, deliberate growth. The universe had time to work, but the 300 early candidates Webb revealed seemed to have achieved comparable masses within only about 500 million years of the Big Bang. That's impossibly fast. To reach those sizes so soon, they would have needed to funnel gas into themselves at breathtaking rates, 10 to 20 times faster than galaxies do today. Vast streams of hydrogen and helium would have had to collapse into compact regions, condensing into billions of suns before the cosmos had even properly cooled. Dark matter halos, invisible skeletons of gravity, usually guide this process. They draw ordinary matter inward, creating pockets where galaxies can form. But according to standard cosmological models, halos massive enough to anchor large galaxies shouldn't yet have existed at such early times. The ones that did exist should have been small, capable of holding only dwarf-sized systems. So how did these immense galaxies appear when the scaffolding to hold them shouldn't have been there? One idea is that they formed in exceptionally rare and dense regions of the early universe, places where matter was unusually concentrated due to random quantum fluctuations in the Big Bang's energy field. If a galaxy was lucky enough to form inside one of these rare peaks, it would have access to far more gas than average. But even then, the numbers don't quite fit. The densest peaks predicted by standard models still don't offer enough material to explain the sheer masses these galaxies seem to hold. Something more must have been at work. Perhaps the efficiency of star formation itself was radically different. Modern galaxies are messy and wasteful. Much of the gas that falls into them is expelled again by stellar winds, supernova explosions, or active black holes. Only a small fraction of infalling gas becomes stars. But in the early universe, the conditions may have been far more favorable. The gas was denser, purer, and cooler. It may have collapsed more directly into stars before feedback processes had time to blow it away. If these ancient galaxies converted gas into stars 2 or 3 times more efficiently than modern ones, they could have built mass astonishingly fast. Another possibility is that the early cosmos was far more dynamic, with frequent mergers between smaller proto-galaxies. If several infant galaxies formed close together, gravity could have drawn them into one another almost immediately. Each collision would create a larger, more luminous system, several small sparks merging into a single blaze. In the densest pockets of the early universe, this could have happened repeatedly, giving rise to massive galaxies long before theory says it should be possible. Yet even these explanations strain the models. They rely on rare conditions, perfect timing, and unusually efficient star formation. So perhaps some of the 300 objects aren't true galaxies at all. If some are actually quasars or black hole-powered systems, their extreme brightness could trick our measurements. A quasar, a supermassive black hole devouring matter at ferocious speed, can easily outshine billions of stars, creating the illusion of a huge galaxy where only a compact, energetic core exists, but if even a fraction of the 300 are genuine massive galaxies, then the mystery remains. The universe somehow managed to gather and ignite billions of solar masses worth of gas in a fraction of the expected time. It's as though the cosmos skipped a few steps in its own construction manual. The logistics simply don't add up under standard physics. Something fundamental, either in how matter was distributed or how efficiently it formed stars, must have differed in the young universe. And that's where accurate distance measurements become crucial. Because if we've misunderstood how far away these objects truly are, we may also have misunderstood how early they existed. Measuring distance in the universe sounds simple, but in practice, it's one of the most delicate tasks in astronomy. There are no signposts, no cosmic rulers floating in space. Everything depends on decoding the light that reaches us. The key lies in redshift, the stretching of light by the expanding universe. As space itself expands, it stretches the wavelengths of photons traveling through it. The more the light is stretched, the higher its redshift, and the farther back in time it originated. Astronomers express this as a number, Z. A galaxy at redshift 0 is here and now. At redshift 1, the universe was half its present size. At redshift 7, it was about 1/8 its current size. At redshift 10, it was just 1/11th, a tiny, newly born cosmos. Early analyses used the dropout technique to estimate redshifts for the 300 candidates. This method compares how an object's brightness disappears in certain wavelengths as light is absorbed by intergalactic hydrogen. It's useful for rough estimates, but not exact ones. Later, astronomers refined the numbers through spectral energy distribution fitting, comparing observed light across multiple wavelengths with theoretical models. That analysis showed a surprising divide. Roughly 2/3 of the objects appeared closer than first believed. At redshifts between 1 and 4, meaning they existed between 2 and 12 billion years ago. Still ancient, but not cosmologically impossible. The remaining third, however, stayed stubbornly distant. True cosmic enigmas, existing less than 1 billion years after the Big Bang. And it is those few, the earliest, brightest, and most massive, that continue to challenge everything we thought we knew about how the universe built itself. But galaxies don't build their mass overnight. Our Milky Way, for instance, accumulated its hundreds of billions of stars gradually, over billions of years. Each generation of stars, each small merger with a neighboring galaxy, slowly added more matter to the growing spiral. It was a patient process, paced by the physics of cooling gas, gravity, and time itself. Yet the 300 early galaxies discovered by James Webb seem to have raced past that cosmic speed limit. They appear to have gathered immense quantities of matter, tens or even hundreds of billions of suns worth, within just a few 100 million years after the Big Bang. That's like watching a city of skyscrapers rise overnight in a world that has barely invented bricks. To reach those sizes so quickly, these galaxies would have needed to pull in gas at rates 10 to 20 times higher than any seen today. Dark matter halos should have helped funnel ordinary matter inward through gravity. But the problem is, those halos weren't supposed to exist yet at such massive scales. According to every model of structure formation, the early universe simply hadn't had enough time to build such deep gravitational wells. So, how could it have happened? One idea is that these galaxies formed in rare, ultra-dense regions of the early cosmos, statistical peaks, where matter happened to be more concentrated than average. In those few privileged pockets, the abundance of gas could have accelerated formation. But even that explanation stretches the numbers. The density fluctuations in our best cosmological models can't fully account for so much mass so early. Another possibility lies in star formation efficiency. Modern galaxies are surprisingly wasteful. Only a small fraction of the gas that falls into them ever turns into stars. The rest gets heated, blown out, or recycled by stellar winds, supernovas, and black hole outflows. But in the early universe, denser, simpler, and more pristine. This feedback may have been weaker. If that gas was converted into stars with much greater efficiency, it could explain the rapid buildup. Mergers might have helped too. If numerous small proto-galaxies formed close together, gravity could have quickly pulled them into one larger system. Instead of a slow process of gradual growth, it could have been a violent, chaotic assembly, a swarm of young galaxies colliding and fusing in the dark. There's also the chance that some of these objects are imposters. If they're actually quasars, supermassive black holes feeding on matter and glowing brilliantly, their brightness might have fooled astronomers into thinking they're massive galaxies. A quasar can mimic the light of billions of stars while containing only a fraction of their mass. Still, even if only a portion of these 300 candidates turn out to be true, fully formed galaxies, the mystery remains. Somehow, the infant universe, only 500 million years old, concentrated unimaginable amounts of gas into small regions and converted much of it into stars faster than any model predicts. The logistics simply don't fit standard physics. Something about the early universe's structure, energy, or cooling behavior must have been fundamentally different. But before we can solve that puzzle, we have to answer a simpler one. Are these galaxies really as far away, and therefore as ancient, as they seem? Measuring distances in the universe isn't as straightforward as it sounds. There are no cosmic mile markers or "you are here" signs floating in space. Everything we know about how far away something is comes from analyzing its light. Specifically, how much that light has been stretched by the expansion of space itself. That stretching is called redshift. The farther away a galaxy is, the more its light has been stretched toward the red end of the spectrum. The amount of that stretching, its redshift, or Z, tells us how much the universe has expanded since that light was emitted. A galaxy at redshift 0 is here now. At redshift 1, we're seeing it from a time when the universe was half its current size. At redshift 10, we're looking back to when the cosmos was barely 1/11th of its present size, a few hundred million years after the Big Bang. Initial analyses using a technique called the dropout method suggested that many of the 300 galaxies had redshifts above 7, meaning they existed less than 800 million years after the universe began. But these early estimates are only rough guesses. To refine them, astronomers use spectral energy distribution fitting, comparing the brightness of each galaxy across multiple wavelengths to theoretical models of how light should behave at different redshifts. This more careful approach revealed something surprising. About 2/3 of the objects seem to sit at redshifts between 1 and 4. Still distant, but not impossibly early. The remaining 100 or so, however, still show the signatures of extreme redshifts above 7, some possibly reaching 10 or higher. If those measurements are correct, we're seeing light from galaxies that formed when the universe was just 3 to 5% of its current age. That's cosmic infancy. But there's a catch. All of this depends on models of how galaxies should look at those distances. If the early galaxies had unusual properties, different dust content, star types, or chemical compositions, their light could fool us. Some that appear ancient might actually be closer, younger systems behaving in unexpected ways. To confirm their true distances, astronomers rely on a more precise tool: spectroscopy. Instead of just capturing an image through colored filters, spectroscopy spreads a galaxy's light into a rainbow and analyzes its atomic fingerprints. Every element leaves a unique pattern of emission or absorption lines. By measuring how far these lines have shifted toward the red, astronomers can determine a galaxy's exact redshift and know for certain how far back in time they're looking. Spectroscopy also reveals what the object actually is: a star-forming galaxy, a quasar, or something stranger. But the process is slow. It can take hours or even days of telescope time to collect enough light for one clear spectrum. And with hundreds of candidates, that's a massive undertaking. Over the next few years, scientists will focus Webb's instruments on dozens of these mysterious red galaxies. Spectroscopy will confirm which are truly ancient and which are imposters, revealing their chemical compositions, stellar populations, and physical natures. Until then, the mystery remains suspended between wonder and doubt. But even the preliminary evidence is enough to shake the foundations of cosmology. Because if these galaxies are real, if they truly existed so soon after the beginning, then our understanding of how stars, matter, and time itself evolved will have to change. Now imagine what these early galaxies achieved. If they truly contained between 50 and 100 billion solar masses in stars, and managed to build those stellar populations within just 500 million years, their average rate of star formation must have been staggering. Roughly 100 to 200 solar masses per year, sustained over 500 million years. That's already near the upper limit of what we see in the most active starburst galaxies today. But that's only the starting point. Massive stars live fast and die young, burning through their fuel in only a few million years before exploding as supernovas. To keep their total stellar mass growing, these galaxies had to form new stars faster than old ones were dying. When that ongoing cycle of stellar birth and death is factored in, the required star formation rate climbs even higher, perhaps 300 to 500 solar masses every year during their peak. That's several times greater than the most extreme rates observed anywhere in the modern universe. The question then is, how could the early cosmos sustain such furious growth without feedback processes? The winds, explosions, and radiation from massive stars, shutting it all down. One idea is that feedback itself was weaker or less effective in the early universe. The primordial gas was denser and more tightly bound by gravity, making it harder to blow away even under the onslaught of supernovas and stellar winds. Another explanation involves efficiency. Perhaps the first galaxies were extraordinarily good at turning gas into stars. In galaxies today, only a few % of available gas becomes stars before feedback halts the process. But in those early epochs, efficiency might have reached 10 or even 20% before the first feedback effects could react. A third idea focuses on gas inflow. Maybe fresh streams of cold gas continuously flowed into these galaxies from surrounding space. Even if feedback expelled some material, new gas would constantly replenish it, allowing star formation to continue unabated. Such continuous inflow would require unusual cosmic geometry, dense filaments funneling matter straight into the galaxy's heart, something rare in the modern universe, but perhaps common in the early web of matter. Some astronomers suspect that star formation wasn't steady at all. Instead, it may have occurred in intense bursts, short-lived explosive periods separated by calm interludes. Each burst could have converted huge amounts of gas into stars over just a few million years before shutting down temporarily. Repeated cycles of such bursts could, over time, build the massive stellar populations Webb observes. Yet even this explanation struggles. Those bursts would have to be extraordinarily powerful and frequent to reach the observed masses in so little time. Whatever mechanism was at work, the early universe must have been a place of astonishing productivity, pushing the limits of what physics says should be possible. Between 400 million and 1 billion years after the Big Bang, the cosmos underwent one of its greatest transitions, the epoch of reionization. Before that period, space was filled with neutral hydrogen, an invisible fog that absorbed most ultraviolet light. The first generations of stars and galaxies began to emit intense UV radiation, slowly ionizing that hydrogen, stripping electrons from atoms and clearing the cosmic mist. For the first time since the universe's dark ages, light could travel freely. The 300 mysterious galaxies discovered by Webb should have existed right in the middle of this process, or perhaps before it even began. After the universe cooled following recombination, around 380,000 years after the Big Bang, hydrogen atoms formed, trapping light and rendering space opaque. To reverse that, something had to provide enough energy to rip those electrons free again across the entire cosmos. That something was starlight. The hot, massive stars in early galaxies produced vast numbers of ultraviolet photons, each energetic enough to ionize hydrogen. As more galaxies ignited, they filled the universe with bubbles of ionized hydrogen, each expanding outward. Over hundreds of millions of years, those bubbles grew, merged, and eventually cleared nearly all the neutral gas between galaxies, ending the dark ages. Astronomers estimate that reionization was largely complete by about 1 billion years after the Big Bang, but the 300 Webb galaxies might have existed long before. That point, around 500 to 700 million years after the beginning, when the universe should still have been shrouded in neutral gas. Their light, therefore, had to pass through the remnants of that fog to reach us. If these galaxies were as bright and as numerous as they appear, they should have had an enormous impact on reionization itself. 300 luminous galaxies, each pouring out UV radiation, would ionize tremendous volumes of hydrogen around them. And if the observed region is representative of the wider universe, there could have been thousands more like them scattered across the sky. Together, such galaxies might have driven reionization far earlier and faster than standard models predict, perhaps completing it just 600 million years after the Big Bang, hundreds of millions of years earlier than expected. But that idea runs into conflict with other observations. Studies of distant quasars, brilliant beacons powered by supermassive black holes, reveal absorption patterns in their light caused by neutral hydrogen. Those patterns show that significant amounts of neutral gas still existed as late as 800 million years after the Big Bang. In other words, reionization wasn't finished early, It proceeded roughly on schedule. So if these early galaxies really existed in large numbers, why didn't they ionize the universe faster? One explanation is that most of their UV radiation never escaped. Dust and dense gas inside the galaxies could have trapped much of that light, absorbing it before it ever reached intergalactic space. Or perhaps the galaxies were surrounded by thick cocoons of neutral hydrogen that soaked up the escaping photons. In either case, they would appear bright to us, but contribute little to the overall ionization of the cosmos. Another possibility is simpler. Maybe these galaxies aren't as common as they seem. The Webb survey covered only a minuscule patch of sky. If that region happened to be unusually rich in galaxies, a cosmic coincidence, the overall population could be far smaller, reducing their collective effect on ionization. Or perhaps the redshift estimates themselves are off. If most of these objects actually sit at lower redshifts, they would have existed later, when ionization was already well underway or complete. In that case, they wouldn't need to explain the early ionization at all, because they weren't there yet. There's also a more radical idea. Maybe reionization wasn't uniform. Perhaps some parts of the universe cleared early, while others stayed neutral longer. The quasar measurements that tell us about ionization sample only narrow sightlines through space, specific paths that might pass through regions where the fog lingered longer than average. Other regions, where galaxies were densely packed, might have become transparent far earlier. Ionization remains one of the least understood eras in Webb Space Telescope. These 300 massive, impossibly early galaxies may be forcing us to rethink some of its core assumptions. To see what's at stake, we need to understand what lambda CDM actually says. Lambda represents dark energy, the mysterious pressure driving the universe's accelerating expansion. CDM stands for cold dark matter, the invisible gravitational framework that allows galaxies to form and grow. Along with ordinary matter, radiation, and Einstein's general relativity, these ingredients together form a model that has long matched the universe we see. According to that model, the early cosmos was almost uniform, a smooth sea of matter with only tiny fluctuations in density. From those faint ripples, gravity gradually built the vast cosmic web we see today. But if Webb's galaxies are real, that gradual process might not have been gradual at all. Something, somewhere, may have supercharged the birth of structure in the very first dawn of time. These tiny variations came from quantum ripples, frozen into the universe during the first moments after the Big Bang. Minute fluctuations in density born during cosmic inflation. Over time, gravity magnified those ripples. Slightly denser regions pulled in more matter, growing denser still, while emptier regions thinned out. This process created the first scaffolding of structure across the cosmos. According to the standard lambda CDM model, this growth happens from the bottom up. The smallest objects, dwarf galaxies, form first, just a few 100 million years after the Big Bang. These small galaxies then collide and merge, slowly building up larger and larger systems. Massive spirals and ellipticals like our Milky Way shouldn't fully form until billions of years later. Lambda CDM predicts not only how fast structure grows, but also how many galaxies of each mass should exist at different cosmic times. In the early universe, we should see countless small galaxies and almost no large ones. Only as time passes and mergers accumulate do the giants appear in significant numbers. Cosmologists can calculate this mass distribution precisely by simulating how gravity shapes matter across cosmic time. And remarkably, those predictions have held up. Surveys of nearby galaxies fit the model almost perfectly. The cosmic microwave background, the faint relic light from 13.8 billion years ago, also matches the same theoretical framework. For decades, lambda CDM has explained nearly every observation we've made about the large-scale universe. But now, the 300 ancient galaxies discovered by James Webb threaten to break that success story. If even a portion of them are truly massive and truly ancient, they exist in numbers that lambda CDM simply does not allow. According to the model, galaxies with tens of billions of stars should be vanishingly rare only 500 million years after the Big Bang. Yet Webb found hundreds in just a narrow slice of sky. That shouldn't be possible. There are a few ways to make sense of this. The simplest is observational. Maybe the distances to many of these galaxies have been overestimated. If their redshifts turn out to be lower, then they're not as early or as revolutionary as they seem. Spectroscopic follow-up will clarify that, Another, subtler explanation is that lambda CDM is mostly right, but missing some ingredients. Perhaps dark matter isn't perfectly cold. If it has a slightly warm component, particles moving a bit faster than expected, it could trigger structure formation earlier in some regions. Or maybe quantum fluctuations during inflation were stronger in rare spots, giving those patches of space a head start in galaxy growth. Then there's the possibility that our understanding of star formation itself is incomplete. Lambda CDM handles gravity and dark matter beautifully, but it doesn't simulate what happens inside galaxies, the chaotic, feedback-driven physics of gas, dust, and newborn stars. If early star formation was far more efficient than we think, if primordial, gas clouds turned into stars at 10 or 20 times today's rate, then galaxies could have built up mass astonishingly fast without breaking the model's larger framework. But the most radical option is that lambda CDM itself needs to be rewritten. Maybe dark matter behaves differently under extreme early universe conditions. Maybe dark energy, the mysterious force accelerating cosmic expansion, was stronger or weaker back then. Or perhaps even Einstein's general relativity, the foundation of modern cosmology, requires modification to explain these early structures. Most cosmologists hesitate to go that far. Lambda CDM has survived every major test for decades. It's the most successful cosmological model ever built, but the Webb data have undeniably shaken confidence. If further spectroscopy confirms that many of these galaxies are truly massive and truly ancient, then something in our cosmic recipe must change. As astrophysicist Joel Leger put it, finding these objects challenges current ideas about how galaxies formed in the early universe. In the careful language of science, challenges is code for this doesn't fit what we expected at all. Over the next few years, new Webb observations will decide the fate of our deepest cosmological theory, whether lambda CDM survives intact, demands major revision, or faces a crisis that calls for new physics entirely. And in the midst of this debate, one radical possibility has begun to emerge. What if these impossible galaxies had help? From the universe's very first seconds, some cosmologists now suspect that primordial black holes, forged in the violent chaos just after the Big Bang, might have acted as the seeds of these early giants. It sounds like science fiction, but the physics might make it real. Primordial black holes are not like the ones born from dying stars. Stellar black holes require stars to exist first. These, if they exist, would predate the first light itself. They might be the forgotten architects of the earliest galaxies. Primordial black holes were born in a completely different way from the ones we know today. During the first fraction of a second after the Big Bang, the newborn universe was a seething ocean of energy, violent, unstable, and expanding at incomprehensible speed. In that chaos, tiny fluctuations in density could have grown so extreme that some regions collapsed under their own gravity, forming black holes directly out of pure energy and matter. These were primordial black holes, cosmic fossils from the first instant of creation. Unlike black holes formed from dying stars, these primordial versions could have appeared in any size. Some might have been minuscule, weighing less than a mountain. Others, unimaginably massive, containing thousands or even millions of solar masses. And because they formed almost instantly after the Big Bang, they were present from the very dawn of time, ready to influence everything that followed. Now picture one of these ancient black holes drifting through the darkness of the early cosmos, embedded in a dense cloud of hydrogen gas during the cosmic dark ages. Its immense gravity pulls the gas inward, spiraling it ever faster until friction heats it to millions of degrees. The glowing gas radiates energy outward, bathing its surroundings in heat and ultraviolet light. That radiation can change everything nearby, heating, compressing, and even ionizing the gas around it. The results would be complex and profound. In some regions, the radiation's shockwaves could trigger star formation, squeezing distant pockets of cold gas until they collapse into newborn stars. In others, the same energy could suppress formation by blowing gas apart. The interplay of heating and compression would create a patchwork cosmos, bursts of light surrounded by expanding darkness. But primordial black holes could do more than light fires. They could build the first galaxies themselves. Acting as gravitational anchors, their enormous mass would draw gas and dark matter together, creating dense knots that evolved faster than the rest of the universe. A single million solar mass black hole at the heart of a proto-galaxy would dramatically accelerate how quickly matter gathered, feeding an early burst of star formation, instead of waiting hundreds of millions of years for dark matter halos to merge and grow. These galaxies could have skipped the line entirely, born early, massive, and bright. This idea fits intriguingly with what James Webb has seen. We already know that supermassive black holes, with billions of solar masses, existed astonishingly early. Telescopes have spotted quasars at redshifts above 7, meaning they were already blazing less than a billion years after the Big Bang. Growing such monsters from ordinary stellar remnants in that short time seems almost impossible. Primordial black holes, on the other hand, could have started large, providing ready-made seeds for rapid galactic growth. If these ancient black holes seeded the first galaxies, several of the universe's biggest puzzles suddenly make sense. The incredible brightness of early galaxies could come from black holes actively feeding on gas. The accelerated buildup of stellar mass could result from their gravitational pull drawing matter inward. Even the strange reddish colors of some galaxies might arise from heated dust illuminated by black hole radiation. But for all its elegance, this theory faces major challenges. We've never directly detected a primordial black hole. They are theoretically possible, but no definitive evidence has ever been found. Detecting them would be extremely difficult. Unless they're actively consuming matter, they emit no light, remaining invisible against the cosmic background. They could drift silently through space, hidden in the dark. Another issue is rarity. Observational constraints suggest that if primordial black holes exist, they make up only a tiny fraction of the universe's dark matter. If that's true, it would be hard to explain how hundreds of early galaxies could each have one at their core, unless they're far more common than current limits suggest, or we happen to look at an unusually rich patch of sky. There's also the problem of signatures. Actively feeding black holes give themselves away through X-rays, emission lines, and powerful jets of energy. Some of the 300 galaxies James Webb has found do show hints of such features, but many don't. If all were seeded by primordial black holes, we would expect stronger and more consistent evidence. So for now, the idea remains speculative but compelling. It's the kind of creative leap that arises when observations refuse to fit the models. Primordial black holes might not be the ultimate answer, but searching for them could reveal something deeper about the universe's earliest moments. History has shown that the strangest ideas sometimes turn out to be the most profound. And as astronomers debate the furious, fast-growing galaxies of the early universe, they've discovered another kind of mystery, one that's eerily quiet. Not all of these ancient objects are blazing with light and activity. Some appear to have gone still, to have fallen asleep astonishingly early, shutting down star formation while the cosmos itself was still young. Astronomers call them sleeping beauty galaxies, and they may be just as puzzling as the ones that refuse to stop shining. A dormant galaxy is a strange kind of survivor. It still holds its stars, billions of them, but no longer gives birth to new ones. All the raw material for creation, the cold hydrogen gas that once collapsed into shining suns, has either been consumed, expelled, or heated beyond use. What remains is quiet, a fossil galaxy, its ancient stars aging slowly, their light fading with time. In today's universe, such silent systems are common. Massive elliptical galaxies around us long ago stopped forming stars. Their youthful fires extinguished billions of years in the past. But discovering one in the early universe, when everything should have been alive with growth, is shocking. The first of these, sleeping beauty galaxies, was found. Even before James Webb's full trove of 300 early candidates, astronomers uncovered a galaxy that existed just 680 million years after the Big Bang, yet its light carried no trace of new star formation. Its spectrum told another story entirely. It was made of old stars, some formed even earlier. Somehow this galaxy had raced through its youth, building a massive stellar population almost instantly. And then, for reasons no one can yet explain, it stopped. Since that discovery, more sleeping beauties have emerged. Some of the red galaxies seen by James Webb may not be dusty and newborn as first thought, but aged and dormant instead. Their deep crimson color could come not from glowing dust, but from the collective light of old, cooling stars. Distinguishing between the two possibilities requires detailed spectroscopy, the kind that reveals exactly what kind of stars and elements a galaxy holds. But why would any galaxy fall asleep so early, when the universe itself was barely a billion years old? In the modern cosmos, astronomers know several ways to quench star formation. A supermassive black hole can heat the surrounding gas, preventing it from cooling and collapsing into stars. Two galaxies colliding can disrupt their gas supplies, or a galaxy plunging through a denser medium can be stripped of its fuel by pressure. Yet none of these explanations should have worked well in the early universe. Back then, black holes were still small, unlikely to generate enough energy to sterilize entire galaxies. The cosmic gas between galaxies was thin and diffuse, too weak to strip away material. Even galaxy mergers, though chaotic, usually ended by triggering more star formation, not ending it. So what changed? One idea points to the first generation of massive stars. If an early galaxy formed an enormous burst of them all at once, the combined force of their supernova explosions could blast out nearly all remaining gas, leaving behind only the stars that had already formed. The result, a brilliant but brief life, followed by centuries of silence. Yet this scenario requires a fragile balance. The galaxy must lose most of its gas but somehow keep the stars bound together. Another possibility is environmental starvation. Perhaps these galaxies were born in regions of the cosmos that quickly ran out of gas. Areas where neighboring galaxies or intense radiation ionized and consumed the hydrogen nearby. Starved of fresh material, they simply went dark. Some astronomers wonder if these galaxies are not truly dead, only resting. They could undergo cycles of star formation and dormancy, flaring up when new gas falls in, then fading again when it's spent. If that's true, the galaxies we now call sleeping might one day awaken. Given another few hundred million years, a quiet galaxy at redshift 8 might reignite by redshift 6, birthing new stars from newly cooled gas. But if many galaxies really did fall asleep so soon, that changes how we understand cosmic history. Every dormant galaxy locks away mass that no longer contributes to later star formation, shaping the growth of the universe in hidden ways. Each one represents a dead end, a branch of evolution that stopped too early, and yet not all may stay dead. Some may have flickered back to life later, pulling in fresh gas and reigniting their stars. These galaxies could be the cosmic phoenixes, reborn after eons of quiet. The existence of sleeping beauties, side by side with violently active star factories, paints a picture of the early universe far more complex than astronomers imagined. Instead of a smooth, uniform growth, the cosmos seems to have experimented. Some galaxies burning bright and fast, others flaring briefly and falling into stillness. Among the 300 mysterious galaxies James Webb revealed, 3 stand apart. They are massive, impossibly red, and far too developed for their age. Astronomers have started calling them the red monsters. Objects so extreme that even the most daring theories struggle to explain how they could exist so soon after the dawn of time. They are so vast, so impossibly massive, and so ancient that they make the other early galaxies look almost modest by comparison. Each of these 3 red monsters, as astronomers now call them, contains as many stars as the largest galaxies in the modern universe. And yet they existed only about 700 million years after the Big Bang, when the cosmos was still in its infancy. These colossal systems sit at redshifts around 7 to 8, placing them in the era of reionization, when most galaxies were still small, chaotic, and rapidly evolving. By contrast, the red monsters appear fully formed, each holding 80 to 200 billion solar masses of stars, rivaling or even surpassing the Milky Way, which today holds about 150 billion. Finding one such object that early would have been astonishing. Finding 3 in a single patch of sky, within a relatively small survey, suggests they are far more common than theory allows. If this small region contains 3, how many more might be scattered across the entire universe? Possibly thousands, each rewriting the limits of cosmic growth. What makes these galaxies even more disturbing to theory is not only their size, but their efficiency. In the modern universe, galaxies are sloppy builders. They turn only about 10 to 20% of their available gas into stars before feedback. Radiation, supernova explosions, and black hole winds blows the rest away. This inefficiency is a natural brake on galactic growth. The red monsters, however, seem to have ignored every rule. Calculations suggest they converted nearly half of all available gas, 40 to 50%, into stars. That kind of efficiency has never been seen before. It means they somehow bypassed or suppressed the feedback processes that normally limit star formation. As astronomer Steinwitz put it, these galaxies represent a tantalizing puzzle because they appear to have raced through the cosmic obstacles that restrain every other system. Supernovae should have blown their gas apart. Black holes should have heated their surroundings. Yet these galaxies formed with almost reckless speed and precision, building enormous stellar populations before the universe was even a billion years old. Their color, a deep, infrared red, is what first drew attention. This redness could signify heavy dust or an abundance of old stars, but their spectral shapes suggest something more complex. Mature, dusty, possibly even partly dormant galaxies. Some may already have ended their main phase of star formation, glowing faintly with the light of aging stars, long after their brief but furious youth. If they formed through the standard bottom-up model of galaxy evolution, small galaxies merging over time into larger ones, they would represent the merger of hundreds of proto-galaxies. But that's impossible in the available time frame. The universe at 700 million years old simply hadn't existed long enough for that many mergers to occur. Simulations show that even the fastest assembly through collisions couldn't produce such giants so early. The alternative is radical, a top-down collapse, where immense clouds of gas collapse directly into galaxies almost all at once. That scenario defies the LCDM, lambda cold dark matter model, which predicts that small structures form first and combine slowly into larger ones. Yet these galaxies seem to demand just such a reversal of order. Massive structures appearing full-grown while the rest of the cosmos was still assembling its first stars. The implications run even deeper. To hold together such massive galaxies, each would need to reside inside an enormous dark matter halo, perhaps 1 trillion solar masses in total. Building halos that large in such a short time pushes the limits of what cold dark matter physics can produce. It implies the early universe must have been more efficient at clustering matter than we believed, or that our understanding of dark matter itself might be incomplete. Skeptics suggest we may have stumbled upon a statistical fluke, a rare, overdense pocket of the cosmos where matter pooled unusually quickly. The universe is vast enough for anomalies. Maybe we just happened to look in the right place at the right time. But the odds are uncomfortable. Finding 3 of these in one survey field makes coincidence less and less convincing. If they were truly 1 in a billion phenomena, we shouldn't have found any at all. And so, astronomers face a sobering possibility. These galaxies might not be outliers. They might be the vanguard of a hidden population the universe has been keeping secret until now. If that's true, then the red monsters are not just an inconvenience for existing models. They are a crisis. They challenge the deepest assumptions about how quickly matter can organize, how efficiently stars can form, and how early the universe could build complexity. For decades, our cosmic narrative has been a patient one. We believed galaxies grew slowly, merging like drifting continents over billions of years. Textbooks painted the early universe as a gradual dawn, small sparks of light gathering into the first stars, then the first clusters, then the first grand spirals. But the James Webb Space Telescope has turned that story inside out. The discovery of 300 early galaxies, capped by these 3 red monsters, suggests a universe that grew fast, burned bright, and matured far sooner than anyone imagined. Everything we thought we knew about the first chapter of cosmic history, that calm unfolding of creation after the Dark Ages, may have to be rewritten from the ground up. The first stars, those primordial giants, born from pure hydrogen and helium, shone alone in the cosmic dark. They were scattered sparsely across the vast emptiness, each one a lonely beacon in a sea of silence. Over the next few 100 million years, these stellar islands began to cluster, drawn together by gravity's quiet insistence. Small proto-galaxies emerged, fragile assemblies of 10 to 100 million stars each. These were the building blocks of everything that would follow. One by one, they collided and merged, 2 dwarfs becoming one, their stars mingling, their gas clouds colliding, forming new generations of light. Each merger birthed something larger, more complex, more luminous. The universe was constructing itself piece by piece, a delicate, deliberate process of cosmic architecture. By the time the universe reached its first billion years, modest galaxies had begun to take shape. Truly massive ones like the Milky Way were still eons away. This vision of slow, patient growth fit perfectly with every observation and every simulation we had. Hubble's deep field images revealed exactly what we expected. Tiny blue smudges of young, compact galaxies scattered through the early cosmos. The cosmic microwave background displayed faint ripples, minute density fluctuations that would, over time, blossom into stars and galaxies. Computer simulations confirmed the model beautifully. It was elegant, consistent, and deeply satisfying. Then came James Webb, and everything began to unravel. The telescope's golden mirrors captured something the universe was never supposed to reveal: 300 galaxies, burning far too brightly and shining far too soon. Some were sleeping beauties, already old and dormant when the cosmos should have been just awakening. Others, the red monsters, contained as many stars as modern galaxies billions of years older. Suddenly, the entire carefully constructed story of galaxy formation began to collapse. The new picture emerging from Webb's data is one of violence and speed, not patience and grace. The early universe wasn't careful. It was frenetic, a storm of creation where galaxies formed explosively, grew rapidly, and evolved at breathtaking rates. Star formation rates that should have been impossible exceeded modern extremes by factors of 5 or 10. Gas clouds collapsed efficiently, ignoring the physical barriers that should have slowed them. It's as if the early universe skipped the gentle prelude and jumped straight into a cosmic crescendo. The implications are staggering. If massive galaxies existed so early, they must have emitted immense radiation, ionizing the hydrogen fog of the young cosmos far faster than models predicted. The timeline of rionization, the universe's second great dawn, would shift dramatically earlier. These galaxies' stars would have forged heavy elements, carbon, oxygen, iron, far sooner, enriching the intergalactic medium and paving the way for planets and life earlier than expected. Even supermassive black holes, those ancient engines of light, might have formed earlier and grown larger because of this accelerated structure formation. It could explain why Webb and other observatories are finding quasars powered by billion solar mass black holes so soon after the Big Bang. And it doesn't stop there. If some galaxies reached maturity almost instantly, their life cycles would have unfolded differently. They might have exhausted their gas and gone dormant billions of years before others even formed. Their powerful feedback, winds, radiation, and jets might have reshaped their surroundings, influencing how later generations of galaxies formed. Even our understanding of the cosmic microwave background, the ancient afterglow of creation, is under scrutiny. The delicate ripples in that radiation told us how matter should have clumped over time. But if galaxies grew faster and denser than those predictions allow, then maybe we've misread the pattern. Perhaps the early universe contained new physics, forces or particles not yet included in our equations. For decades, we imagined a calm beginning, the universe cooling, matter drifting together, gravity slowly sculpting the first luminous structures. Now we see something more dynamic, more unpredictable. The first billion years weren't tranquil, they were tempestuous, a riot of creation that outpaced every expectation. Even the story of our own Milky Way must be reconsidered. We once thought our galaxy's slow growth was typical, that everything in the universe followed the same steady rhythm. Now we know that wasn't the only path. Some galaxies burned like comets, blazing into existence almost instantly, while others, like ours, took the long road, forming slowly, enduring quietly, and lasting longer. This revelation isn't just about tweaking models. It's about reimagining the entire narrative of creation. The early universe was a far more efficient, volatile, and creative artist than we ever gave it credit for. The old version of history read like a careful blueprint. The new one reads like a storm. And amid that storm lie 300 enigmas, bright, ancient, impossible galaxies that have thrown everything we thought we knew into question. For now, they remain in scientific limbo, beautiful, confounding, and unconfirmed. The next phase is crucial. Astronomers are now preparing spectroscopic observations, the most powerful way to reveal their true nature. Unlike simple imaging, spectroscopy dissects light itself, spreading it into its constituent wavelengths. Each pattern of absorption and emission lines becomes a cosmic fingerprint, telling us the composition, motion, temperature, and most importantly, the age of these mysterious galaxies. Once those spectra arrive, we'll know whether the red monsters, the sleeping beauties, and their 297 companions truly belong to the dawn of time, or whether the universe is playing one more illusion on our eager eyes. Each element in the universe leaves behind its own signature in light, a kind of cosmic barcode. Hydrogen, the simplest and most abundant element, paints a distinct set of lines known as the Balmer series. Oxygen marks its presence with bright traces in both the visible and infrared, while heavy metals like iron produce a dense forest of intricate lines. As light from distant galaxies travels across billions of years, these spectral lines stretch and shift together, pulled to longer wavelengths by the expansion of space itself. By identifying these shifted lines, astronomers can measure the precise amount of redshift, essentially determining how far back in time the light was emitted. This technique, called spectroscopy, is far more accurate than simple imaging. Where broadband photographs give rough distance estimates, spectroscopy can pinpoint a galaxy's redshift to within a fraction of a percent. And for James Webb's 300 mysterious candidates, this is the ultimate test. Spectroscopy will answer the most fundamental question of all. How far away are they really? If the data reveal lower redshifts than first thought, these galaxies are closer, smaller, and less ancient than they appear. Fascinating, yes, but not revolutionary. But if many confirm redshifts above 7, meaning they existed, when the universe was less than 800 million years old, then the entire structure of cosmology will need rewriting. Spectroscopy also reveals what's producing the light itself. Stars leave absorption lines carved by the elements in their atmospheres. Active galactic nuclei, powered by supermassive black holes, glow with fierce emission lines from scorching gas. Quasars, blindingly bright cosmic engines, display entirely different signatures. By decoding these spectral fingerprints, astronomers can tell whether a faint red smudge is truly a galaxy, a quasar, or something never seen before. Chemical fingerprints emerge too. The strength and ratio of spectral lines expose a galaxy's composition, its metallicity. Early galaxies should be nearly pure, built from pristine hydrogen and helium forged in the Big Bang. If one shows signs of heavy elements like carbon or iron, it can't be as old as it seems. It must have lived through cycles of starbirth and death. Spectroscopy also helps reconstruct a galaxy's history. Different kinds of stars dominate at different ages. Young stars blaze with strong hydrogen lines, while ancient populations reveal molecular absorption bands from cooler atmospheres. By combining these details, astronomers can estimate when most stars formed, effectively reading the galaxy's biography written in light. James Webb is already turning its powerful instruments toward follow-up spectroscopy. The brightest candidates come first. They need fewer hours to capture enough light for a full spectrum. Each observation can take between 2 and 10 hours, depending on brightness. With hundreds of galaxies to check, the process will take years. The first results, however, are already trickling in. Some galaxies have been confirmed at astonishingly high redshifts, genuine relics of the universe's first billion years. Others have turned out to be closer imposters, still interesting, but not epoch-shattering. A few even revealed themselves as quasars or other exotic phenomena, not galaxies at all. The picture is sharpening, but far from complete. Future surveys will make this process faster and deeper. James Webb will continue collecting spectra for years, while upcoming giants like the extremely large telescope in Chile will join the hunt, using mirrors nearly 40 meters wide to dissect faint ancient light. Together, these observatories will confirm or disprove the existence of those 300 primordial giants. And when a few of them are finally confirmed, they'll become cosmic laboratories. Astronomers will map their structures, measure the motion of their stars, hunt for the first black holes at their hearts, and trace how their stars were born and died. Each confirmed ancient galaxy will be a time capsule, proof of what the young universe could do when the laws of physics seemed barely settled. But spectroscopy will also bring surprises. Some objects may refuse to fit any known category. Their spectra might reveal odd chemical blends or strange motion, evidence of collisions or unseen companions. And as often happens in science, each new answer may lead to a dozen more questions. Because when we split ancient light into color, we aren't just analyzing galaxies, we're eavesdropping on the first whispers of creation itself. Within the next 5 years, astronomers expect to have definitive spectroscopic confirmation for most of the brightest James Webb Galaxy candidates. That data will decide the question once and for all. Are these 300 galaxies genuine cosmic anomalies that rewrite our understanding of the early universe? Or are they simply mirages created by the limits of our models and measurements? The telescope time is already reserved, the observations scheduled, the The countdown to clarity has begun. When observation and theory collide, science faces its defining test. Either the observations are wrong, or the theory must evolve. In this case, the observations appear solid. James Webb is functioning flawlessly. The photons it gathered truly came from extraordinarily distant objects, which leaves the uncomfortable possibility that our theories, not our instruments, require revision. Perhaps even new physics. Scientists use that phrase carefully. New physics doesn't mean discarding everything we know. It means expanding the boundaries of our understanding. Newton's laws still govern the motion of planets, but Einstein's relativity extended them to realms Newton could never have imagined. Classical physics remains accurate for daily life, but quantum mechanics revealed hidden rules at atomic scales. New physics builds on old foundations. It doesn't erase them. So what could demand such an expansion? Several possibilities stand out. The most direct involves star formation theory. Our models predict how gas collapses into stars based on temperature, gravity, turbulence, magnetic fields, and feedback from supernovae. But perhaps we've underestimated something. Maybe star formation in the early universe operated under entirely different conditions. Denser gas, fewer heavy elements, more efficient cooling. If stars could form 10 times faster back then, galaxies could grow massive far sooner. That wouldn't require rewriting physics, only refining our models. But there are deeper possibilities. Dark matter, for example, remains one of the great cosmic mysteries. We know it exists through its gravitational fingerprints, but we don't know what it's made of. Current models treat it as cold, meaning its particles move slowly and clump efficiently. But what if dark matter has subtle interactions with itself? Tiny collisions or self-attractions that accelerate galaxy formation. That would point toward genuinely new physics, revealing a hidden layer of behavior in the dark sector of the universe. Then there's gravity itself. General relativity has passed every test for over a century. But perhaps, on the largest cosmic scales or in the earliest epochs, it behaves just a little differently. Modified gravity theories suggest that the laws shaping galaxies might not be quite the same as those governing planets. A small change in how gravity works could make structures form faster without invoking dark matter at all. If true, that would be revolutionary. Dark energy offers another avenue. It's the mysterious force driving the universe's accelerating expansion today. But what if it wasn't constant? If dark energy varied in strength or behavior over time, stronger in the past or oscillating with cosmic cycles, it could have influenced how fast galaxies formed and clustered. That would extend physics far beyond our current cosmological constant model. Some physicists are even exploring more radical ideas, modifications, to quantum mechanics or to the inflationary period that set the universe's initial conditions. If quantum fluctuations during inflation were larger or more uneven than we think, they could have seeded bigger density variations, creating the raw material for massive galaxies to appear shockingly early. These possibilities venture into the frontier of new physics, where observation and imagination meet. The crucial question is how far we can stretch existing models before we must admit we've crossed that boundary. If tweaking a few parameters, like star formation efficiency or dark matter clustering, resolves the puzzle, that's ordinary scientific progress. But if every adjustment fails to reconcile theory with observation, then we face a true paradigm shift. That's when the term new physics stops being speculative and becomes necessary. We're not there yet, but we're closer than at any time in modern cosmology, astronomies. History is full of moments like this. The discovery of Neptune explained the odd motion of Uranus within Newton's laws. No new physics required. But Mercury's strange orbit demanded something deeper, leading to Einstein's general relativity and a new era of understanding. The mysteries of unseen mass and cosmic acceleration gave us dark matter and dark energy, concepts that reshaped physics itself. Perhaps these early galaxies will ultimately fit within our existing framework. The LCDM, Lambda Cold Dark Matter model, after a few careful adjustments. Or perhaps they'll mark the beginning of the next great revolution in cosmology, a moment when the universe once again reminds us that it still has secrets left to tell. Or perhaps these galaxies are signaling gaps in our knowledge, hints that we're missing entire layers of reality, new particles, unseen fields, or fundamental laws waiting to be written. The implications depend entirely on what the next wave of data reveals. If spectroscopy confirms that many of these 300 galaxies truly exist at such extreme redshifts, and that their masses are real, the case for new physics will grow almost undeniable. But if most prove closer and smaller than they appear, our current framework survives, bruised but intact. That's how science moves forward. We push theories until they crack, then rebuild them stronger. These galaxies are pushing hard. Whether they'll shatter our understanding remains to be seen. James Webb's discovery of 300 mysterious galaxies poses a haunting question. If we missed these, massive, ancient, blazing structures hiding in plain sight, what else might we still be blind to? The universe is vast beyond comprehension, and our observations cover only the smallest fraction of the sky. It's possible that the cosmos teems with impossible objects, simply invisible to our current instruments. Consider how Webb found these galaxies in the first place. It wasn't luck, it was evolution in our vision. Earlier telescopes like Hubble looked at the same regions and saw nothing but darkness. The galaxies were there all along, glowing faintly in light stretched by the expanding universe into the deep infrared, light that only Webb's instruments could see. They were invisible, not because they were absent, but because we lacked the right eyes. That realization exposures lasting weeks or months. Yet if they exist, they would rewrite the timeline of cosmic dawn itself. And then there are the dark galaxies, hypothetical structures composed mostly of dark matter and gas, with few or no stars. Invisible to ordinary light, they would slip through every optical survey. To find them, we'd need to trace their gravity's pull or detect the faint radio whisper of neutral hydrogen. We may also live in a universe filled with failed galaxies, dark matter halos, where star formation never ignited. They'd be invisible too, detectable only through delicate gravitational lensing or radio mapping. But not all the possibilities are subtle. Some border on the extraordinary. Theoretical physics predicts exotic phenomena that could lurk unseen. Black hole stars, gargantuan objects with black holes at their cores, sustained briefly by radiation pressure. Neutron star clusters born in the high-density chaos of the early universe. Strange quark matter, stable remnants of the first seconds after the Big Bang. Or the elusive intermediate mass black holes, those mysterious objects between stellar and supermassive scales, predicted to exist but rarely observed. The early universe may have produced them in abundance, quietly drifting through space without accretion to reveal their presence. And then there are the holy grails of cosmology, the population 3 stars, the very first generation, forged entirely from hydrogen and helium. No telescope has ever seen one directly. They are the ancestors of all starlight, the forges that created the first heavy elements. Finding even one surviving population 3 star would be a discovery of epochal importance. Other mysteries stretch even further. Primordial gravitational waves, echoes of the universe's birth, may still ripple faintly through space-time. Future detectors could one day hear them, revealing the physics of the universe at energy levels no human experiment could ever reach. Dark matter itself might not be as silent as we think if it occasionally interacts with itself or with normal matter. It might already be leaving faint traces in our telescope data, mistaken for noise. Hidden signals could be waiting in plain sight. Even more exotic theories predict cosmic strings, ultra-thin, ultra-dense filaments of energy left over from the first moments of creation. Detecting one would confirm ideas that border on the mythic. And then there's the wildest of all, pockets of false vacuum, tiny regions where space itself remains trapped in a higher energy state. Most physicists hope they don't exist, because if one ever expanded, it could rewrite reality itself. But if small and stable, they might be out there, quietly coexisting with us, invisible, yet eternal. The point isn't that all these things exist. Most probably don't. The point is that the universe is so much stranger and richer than the thin slice we've explored. Every time we build a new tool or invent a new way to look, the cosmos rewards us with surprises. The 300 impossible galaxies taught us that the early universe wasn't quiet or cautious. It was alive, restless, and astonishingly capable. So what comes next? What hidden realities will the next generation of instruments uncover? James Webb will continue observing for decades if the mission endures, each year probing deeper into the darkness. New telescopes are on the horizon, each designed to look further, sharper, and in wavelengths we've never explored. The discoveries won't stop. Somewhere, Perhaps all across the sky, there are objects that would leave us speechless if we could see them. Galaxies older than galaxies, stars made of quarks, holes in space-time itself. They're out there, waiting for the right eye, the right lens, the right moment of curiosity. The universe has proven, time and again, that it is more imaginative than we are, more diverse than our theories, more profound than our predictions. The 300 galaxies are not just anomalies. They are a message from the cosmos itself, whispering one eternal truth. We still have so much left to discover, and what comes next may be stranger than we can even dream.